This is AP Calculus ABB, Unit 5, Lesson 7. We're finding volumes of rotation by cylindrical shells. And I'm going to revisit the problem I did in the last video. If you recall, what we did here, let's see if I can position this correctly, is we looked at the region bounded by the line y equals x, Okay, so y equals x, and I'm going to let 4 grid marks be 1 unit. And y equals x squared. So this is y equals x. And y equals x squared, which is a parabola, but they have these points 0, 0, and 1, 1 in common. Y equals x squared. Okay. And we're going to rotate it about the vertical line. The vertical line, x equals -1. X equals -1. Okay, so that's my line of rotation. My line of rotation. So I'm going to spin this shape. You can imagine it being placed on like a drill chuck and spinning this. What shape would you see when it spins really fast? What solid would it trace? Okay, well, we know it would mirror itself. There's horizontal symmetry here, and it would end up over here. Okay, so let's draw this line. Okay, and parabola. Okay, all right. Okay, and let's draw the shape it would trace. Grab my ellipse tool. Okay, so we trace this shape here. In fact, let's change the color here. Yellow. Okay, to sketch the solid here. And the bottom would be a circle as well. Okay, the back side would be dotted because it would be not visible. Okay, so we'd have this shape, this funnel type shape, like the cone of shame you put on your dog when he comes home from the vet. One side being flat, the other side being curved. All right, and we're interested in finding the volume. Okay, so the volume. Now last time what we did is we divided this, we cut this, sliced it horizontally, right? I'm going to slice it vertically using a cylinder. Okay, so I'm going to use the cylindrical approach. Okay, and I'm going to imagine this. Let's imagine, if you will, taking a thin slice right here. Okay, that has width delta x in this case, and height h, which we'll come back to. Okay, and imagine that thin rectangle being rotated about the line x equals -1. Okay, that would form this rectangle over here, right? Okay, which is also delta x wide and h tall, and it would form this cylinder, this hollow cylinder. Okay. Here's the inner circle. There's the inner circle as well. Oh, move it. That's what happens when you get too close to something here. Okay. That part would be solid. Okay. All right. Now imagine, if you will, if I took this ring, this hollowed out cylinder, and laid it out, stretched it out, it would form a rectangle, very long rectangle. Okay. That would have thickness, right? And we can approximate it. I realize that the circumference of the inner ring is not the same as the circumference of the outer ring, but delta x is small. And for very, very small delta x's, this can be approximated as a rectangle. Okay, and I know I'm not drawing it very precisely here. But this is delta x. The rectangle is delta x thick. It's h tall, and it's the circumference y. And the volume of this is length times width times height. Circumference times h times delta x. Okay. All right. Now the circumference of this circle here is 2 pi r. Circumference is 2 pi r. So let's fill that in. And actually, let's not fill it in. Let's leave it as is. Because I want to put r in terms of x. What is the radius? What is the radius of this circle? Here's r right here. Well, it is x right there. There's my x. And it is 1. So x plus 1, r, equals x plus 1. That's the radius. So the circumference is 2 pi times x plus 1. Okay, now we have the circumference in terms of x. We need the height of the cylinder in terms of x. Okay, well, h, let's do this over here. H is the top value, which is y equals x, minus the bottom value, which is y equals x squared. So h is x minus x squared. The top coordinate minus the bottom coordinate. Okay, x minus x squared. Okay, so that means my volume of my ring cylinder and hollowed out cylinder is circumference 2 pi times x plus 1 times h, x minus x squared, delta x. Okay. All right. So hopefully that makes sense. The idea of the ring method, cylindrical rings, is that we convert it to finding the volume of a thin, empty ring, right? Where the thickness allows us to approximate the volume as a rectangle. Okay. All right. So let's continue on. So that's the volume of the pink hollowed out cylindrical ring. Okay. Now we want to sum up all of those cylindrical rings for x going from 0 to 1. Right? So the volume, let's put it over here. The volume is the integral from 0 to 1 of 2 pi x plus 1 x minus x squared dx. Okay, because we're going to sum up all these cylinders for all the sum of the little cylinders all the way through from 0 to 1, from x equals 0 to 1. Okay, so let's go ahead and do this. Let's see if we can figure this out. So I can take out the constant 2 pi. Okay, I can multiply through x squared minus x cubed plus x minus x squared dx. A little more simplification, 2 pi. Okay, let's do decreasing order. Negative x cubed plus x squared minus x squared cancels out, plus x. Okay, dx. Now let's integrate. 2 pi. Okay, x to the fourth, 1/4, so negative 1/4 x to the fourth. Okay. Yep. Just checking my progress. However, I do these problems first to make sure I'm getting them right. All right, so x 1/2, x 1/2, x squared. Okay, from 0 to 1. Luckily, 1 is real easy to substitute. Negative 1/4 plus 1/2, and inserting 0 just results in 0. So think of this as 2/4, and this is 2 pi times 2/4 minus 1/4, or 1/4, which is pi over 2. And that is the same volume we found in the previous video using the washer method. Okay? So it's just another tool in our arsenal for finding the volume under rotation. Not slicing with a knife this time, but slicing with almost like a round cookie cutter, right? Where you're cutting increasingly larger cylindrical rings out of it. It's kind of a cool approach. I love it.